Hello, my name is Ayron Gors, and welcome to my Project 3 presentation for CE570. In this project, we were tasked with defining a scalar field, vector field, and tensor field of our choosing on a 3D object of our choosing. Now, since we were allowed to reuse the same object that we defined in our Project 2, I decided to go ahead and reuse my silo. And here are just my lines of code that define the various shapes that make up my silo. The left image there are my lines of code that make up my hollow cylinder, and the right image there are the lines of code that make up my hollow hemisphere that sits on top of my cylinder. If you'd like further explanation of these parameterizations and how I derive them and how the code works, please see my Project 2 presentation that's located on this YouTube channel. So moving on, I'd just like to highlight my scalar field, my vector field, and my tensor field. Now the tensor field is relatively self-explanatory. It's just a symmetric tensor that is defined by 3 numbers across the diagonal and zeros everywhere else. But looking at my scalar field, as you can see in the line of code in the top image there, as well as the text as you can see in the bottom image, my scalar field of my choosing is x1 squared plus x2 squared times sine x3. Now x1, x2, and x3 all correspond to the x, y, and z dimensions respectively. And this scalar field may seem a little arbitrary, but looking at the image that you'll see in the next slide, these scalar fields and these variables that correspond to it are actually akin to reinforcement that I will highlight in the next slide. And the vector field is rather arbitrary, but it is actually corresponding to a sort of failure of my silo that corresponds with the location of the reinforcement, so that when it is actually falling over, it is failing in the locations where reinforcement is rather limited. So moving on, that left image there is just a simple schematic of my silo itself that MATLAB outputted. The middle image is the scalar field that I have represented by density. And as you can see, there's some rather dense zones labeled in yellow. And those locations I like to imagine are corresponding to locations of reinforcement within my silo structure itself. As you can see in that reinforcement schematic on the right, all of those lines correspond to some sort of stability or reinforcement to my structure. And as you can see, there are some columns running up the sides of my silo that correspond to the scalar field, so those locations would be more dense, as well as some rings that are providing further stability and reinforcement wrapped around the silo as you go up. So I like to imagine that the scalar field corresponds to the density and the reinforcement at those specific locations. In my left image here, you can see my vector field on my silo. As you move up the silo, you can see my vectors are gaining in magnitude, which makes sense because as my silo is collapsing, you would expect more of the material at the top of the silo to be displaced from its static location. And as you can see in my middle video playing there, this represents my vector field as a displacement. And you can see my silo in the middle of its collapse. In the far right image that you can see, this represents my tensor field, which is akin to transforming the vectors that you can see in the far left image to new vectors that you can see in my displacement. And this makes sense because you would expect the tensors to be rather larger at the top as more of those vectors are changing location or more dramatically than elsewhere in my silo. In this slide, I'd like to justify my scalar field and vector field displacements. As you can see in my displaced silo to the left, those locations where my silo is failing correspond to locations of rather low reinforcement within my scalar field. And like I was saying before, those locations of rather low reinforcement are the locations as you can see in dark blue or purple there. And as you can see in my reinforcement schematic, those locations are rather low in terms of reinforcement. So I like to imagine that this silo is collapsing realistically. And finally, I'd just like to verify the results that MATLAB is outputting. As you can see in my left image there, this is my hand calculations for my point of choice, which is 5 in the x dimension, 5 in the y dimension, and 20 in the z dimension. Working through my math that you can see that my final result is 33.33, 0.99, and negative 45. And as you can see in my MATLAB code results in that middle image, the 33.331 and negative 45 correspond very strongly to my hand calculations. As well as I just threw in the volume calculations for good measure just to further verify that my code is working appropriately. Thanks for watching.